Welcome to my equilibrium analogy video. So first off, we're going to start by defining equilibrium. What is equilibrium? Equilibrium is when the forward and reverse reactions occur at equal rate. When the concentrations of reactants and products are constant, that's when a chemical equation is in equilibrium. Now we're going to talk about my analogy for equilibrium. We're going to start off with two tables inside a building, something similar to a closed system, because in order for equilibrium to exist, the reversible action must happen in a closed system, just so the products that are formed from reactants will be ready for the reversible reaction. By now, I'm done drawing the tables, and you're probably wondering why the tables are different sizes and shapes. Wouldn't that affect the reaction? The answer would be no, because even though equilibrium means equal, it doesn't necessarily mean that everything in the reaction needs to be equal. So mostly it doesn't matter if the volume or of the product and reactant are equal or not. For this video, we're going to have two different colored dots to represent the people in my analogy. A pink one to symbolize the reactants and a green one to symbolize the products. My analogy is that we have two parties sitting at different tables at a reservation-only restaurant. But every few seconds, someone will feel like the table they're sitting at is crowded. They look around and they see the table beside them has more space and want to get up and move. For example, we have one person here feel very uncomfortable because the table is too crowded. They look over to the other table beside them and see that they have a vacant spot, so they stand up and go join the other table. This happens both ways. When the pink dots move over, it means reactants are turning into products. When the green dots move over, the products are reversing back to reactants. This continuously keeps happening as both parties just want to be at a table that's not as crowded. And sometime they'll all be sitting at the same table again, or the number of dots at a table would be balanced, and no matter where they all move, there will be the same ratio because their forward and reverse rates are constant. A thing to notice is that just because they move to another table doesn't mean they change anything. Not their clothes, not the color of their clothes, etc. Just like how macroscopic properties are constant in equilibrium. So let's say this place is super fancy. You need to book it a month back for a table. And since everyone that reserved arrived, the restaurant's doors are closed, creating a closed system. If you open the door and someone leaves, a party will be missing an individual. But that's okay because equilibrium will always try to reach equilibrium again. So if that person left, someone within the party would offer to call someone else, just so they don't waste the spot. But the thing about disturbing the equilibrium is you never know how long it takes for it to reach equilibrium again. Just like you wouldn't know how long that friend's going to take before they come in and fill up that spot that your friend had left before. It could be traffic, it can be a lot of other things that are stopping them. So next, we're going to draw a graph. The graph is a number of people at table versus time graph. With our y-axis, it's number of people at a table, and with our x-axis, it's time. The number of people at table 1 will start at a high point because they had more people, and then fall later on, and it will be the forward rate. Whereas the number of people at table 2 will start at a low point and rise because they gain people, representing the reverse rate. Eventually, they'll all be equal and numbers won't change. That's all for my analogy video, and thanks for watching!